Hey guys, today we're going to talk about two astronomers. These guys are both really influential with a heliocentric model, and this is where we're going to get into some of the math today. So the two astronomers we're going to talk about today, we have Johannes Kepler and Isaac Newton. So Kepler is the first one we're going to talk about. So Kepler is around the same time as Galileo. So as Galileo is getting, as the church tells him he can't continue his view of heliocentrism, Galileo is forced to change his mind and say he doesn't believe in heliocentric theory. As he's doing that, Kepler is actually making his his observations for his three laws of planetary motion. So Kepler is a German astronomer, mathematician, and astrologer who actually works with Tycho Brahe. So Tycho Brahe, we talked about him yesterday. I consider him to be one of the most influential astronomers out there with what he did, and he's very kind of a crazy guy. I talked to you the other day about how he died. Actually, at the time there were actually two theories about how he died. A lot of people said it was his bladder that exploded, and then other people actually think Johannes Kepler actually poisoned him. We now know today that it was actually his bladder exploding, and it wasn't Johannes Kepler. And the reason people think Kepler actually poisoned him was because the two are known not to get along very well because they're kind of exact opposites. So Tycho Brahe was more of like a party animal, whereas Johannes Kepler liked to keep to himself, and he really enjoyed just sitting at home and studying his books and doing math equations. So they're not really alike, but they were both very very famous and important for, like we said, this heliocentric model that we're talking about. So Johannes Kepler, he establishes three laws of planetary motion. We're going to go over those three laws. So this pretty much explains his laws right here. So his first law, if you look at the shape here, so you should notice that the shape here, it's very ovally. So we call that shape, it's called an ellipse. Hopefully you remember this from your math classes you've taken. So this is an ellipse, an oval shape. And what Kepler says is, he says planets, all objects actually, objects move around the sun in an ellipse. And the sun is at one of 2 points. So the 2 points the sun could be at are called focus points, plural, we're going to call them foci. And the sun is at one of those foci. Notice the sun is not in the center. It is off on one of those foci points. That's his first law. His second law, and I'm going to go over these in more detail as we go here, but this is just to get started. I'm just telling you what they are. His second law says equal area and equal time. So if you notice here, you see there's these letters, and we'll start here with A to B, and then we go C to D, E to F, and G to H. Well, this ellipse here represents an object orbiting around the sun, and so it looks like pie pieces almost. So here's a question for you. If this was pie or cake, would you rather have this piece of pie, this piece of pie, this piece of pie, or this piece of pie? Which one looks like it's going to give you more pie out of those four pieces? And the answer is they're all the exact same amount of pie. This one, it doesn't look like it'd be as much because it's so skinny, but it's a lot longer. This one over here looks like it might be the best because it's really fat, but notice how short it is. So his second law says equal area and equal times. So I'll talk more about that in a minute. And then his third law is just a math equation. It's p squared equals a cubed. So that's what we're going to talk about with Johannes Kepler. So this is who Kepler reminds me of. So Kepler and Ned Flanders, if you've ever seen The Simpsons, I know he's a cartoon character, but every time I think of Kepler, that's who I think of. So this is Kepler, and he's, I put ellipses here because that's what Kepler's always thinking about. And then this is good old Ned. Hi diddly ho, neighbor. That's the Simpsons, Homer Simpson's neighbor. So yeah, they kind of have the same stash, same hair. So that's who I think of, just with his mannerisms and how he acts. I just think Kepler would be a lot like that. So here are the three laws of Kepler in order. We're going to have to know which one's the first law, which one's the second law, and which one is the third law. So first law says orbital paths of objects are ellipses with the sun at one focus point. I told you there's two focus points. An ellipse is a oval, so it's not a perfect circle, it's an oval shape. We said Kepler's second law, equal area and equal times. I'll go over what that is in more detail coming up. And then third law, capital P squared equals little a cubed. That's the orbital period squared equals the length of the semi-major axis cubed. So he used these three laws to describe how planets move around the sun based on observations. And he didn't make those observations. Tycho Brahe made the observations. And when Tycho died, Kepler got all of Tycho's data and used it to establish these three laws of planetary motion. Now, Kepler is also very influential with Newton. Newton actually says Kepler's equations helped him come up with his three laws of motion with gravity, really gravity. So Kepler was influential to Newton when he figured out the formula for gravity, which we'll talk about later on in this lecture. So Kepler's first law, the orbital path of planets are ellipses. They're elliptical with the sun at one focus. So we went over this already. Notice the shape is very ovally, like an egg, and then there would be the sun. It is not in the center. It is at one of two focus points. There's a focus point here. There's probably another one right over here. That's Kepler's first law. Make sure you understand that. Make sure you know that word ellipse. Please don't mess up these words. A lot of people get ellipse, ecliptic, and eclipse messed up. So an ellipse is what we're talking about here. It's just the shape that is made when a planet orbits around the sun. It's an ellipse. Remember that an eclipse happens. You have solar and lunar eclipses. That's not the same thing. And then earlier in a prior lecture, we talked about the ecliptic. The ecliptic is the path the sun takes across the sky, even though we know today that the sun isn't actually moving, it's just the earth moving. But it looks like the sun is moving. So please don't mess up those three words, ecliptic, eclipse, and ellipse. We are talking about ellipses today. So that's Kepler's first law. So there's the sun. And then there's Chef. You can see Chef there. He's orbiting around the sun. And notice where Chef is over here. He's far away from the sun. We'll talk about what that's called coming up in a minute. If you want to draw an ellipse, this is just what showing you how you draw an ellipse. So you just take two push pins, you put them a distance, you have a distance between them, you attach string around them, and then you can take a pencil, you can see how it makes like a triangle, and you just keep the string nice and tight, and then you can just move your pencil around the string, and it makes an ellipse. You're not going to need to do that or anything, but that's just showing you how to do it. You are going to need to know the parts of an ellipse. So here you can see two focus points. Plural of focus points is called foci. Okay, and then there's two axes. There's two axes in a ellipse. You've got the large axis going all the way across. So from this point in the orbital path to this point in the orbital path, that's called the major axis. And then over here, from this point of the orbital path to here, that's called the minor axis. So you got a major axis and you have a minor axis. Half of the major axis is called the semi-major axis, and half of the minor axis is called the semi-minor axis. We're not going to really use the minor axis, but we are going to use the major axis with the semi-major axis. So semi means just think of half. So half the major axis is the semi-major axis. That's important because when we deal with averages, so if the sun is at one of these two focus points, we're going to be talking about when a planet is going around the sun. We usually mention the average distance away a planet is from the sun. And that average distance a planet away is from the sun would be the distance, the length of the semi-major axis. So the average distance a planet is away from the sun is the length of the semi-major axis because it's an average. You're going to need to know that. Okay, so this formula here deals with Kepler's first law. So the first law, it deals with the orbital path of objects moving around the sun as being an ellipse. And this formula of eccentricity tells you how elliptical the orbit actually is. So we see here the formula is eccentricity equals the distance between foci, so those two focus points, the distance between them, divided by the length of the major axis. Just showed you what the major axis is on the last slide. Now, what we're going to be doing is we're going to be dividing a distance by a length, or also known as another distance. So if we're dividing a distance by a distance, what is our unit going to be? Eccentricity is not going to have a unit because the units are going to cancel out in the actual formula. So whenever you're dealing with eccentricity, it is just a number, and it does not have a unit to it. So when we're doing a couple examples coming up, make sure you realize that there is no unit for eccentricity because we're dividing a distance by a distance. Distance and length, we consider the same thing. So our distance and length that we're talking about for these problems, anytime we're dealing with space and planets away from the sun, the distance is called an AU, which means an astronomical unit. I've got a slide coming up later on where I tell you what that is. We're going to need to know the average distance away the Earth is from the sun, because that's 1 AU, then that's equal to 93 million miles. You're going to need to know that number. 1 AU, 1 astronomical unit, is equal to 93 million miles. So let's try an example here coming up. So the eccentricity of Jupiter's orbit is 0.018. Notice there is not a unit for eccentricity. Its major axis is 22.4 AUs. Again, an AU is an astronomical unit. 1 AU equals 93 million miles. That's a long distance. What is the length of the distance between the two foci in AUs? So if we're looking for the distance between the two foci, we know, and we're given the eccentricity, we know we're going to use the eccentricity formula to solve for the distance between the two foci. So let's try it. So there's our formula. Eccentricity equals distance between foci divided by the length of the major axis. So let's plug our numbers in now. So we have 0.018 equals the distance between the foci divided by the length of the major axis, which is 22.4 AUs. So we're looking for the distance between foci. So how do we get this distance by itself? Well, if we're dividing over here, 22.4 AUs is on bottom. We're going to have to multiply each side by 22.4 AUs. So we do that, we get foci distance equals 22.4 times 0.018, and we get the foci distance equaling 0.4 AUs. 0.4 AUs. So that's our first example of eccentricity. Okay guys, keep in mind for eccentricity, the more ovally the shape is, the more elliptical it is, the greater the eccentricity. So the lower the eccentricity, the more spherical the planet will be. So if it has an eccentricity of 0, it means it is a perfect sphere. So as the eccentricity increases, the oval shape increases as well. And again, we call that the eccentricity, or how elliptical the orbit is. So take a look here. So here, which one is most eccentric? So right here, you have the TIE fighter, and here you have an X-wing. So which one of these would be stretched? Which one is more oval shaped? Which one is more elliptical? Whichever one is more elliptical would be the most eccentric. So based on this, if you look here, this one looks like it's more of an oval shape than this one. Therefore, the X-wing would be the most eccentric here. It would have a greater eccentricity. So that's Kepler's first law of planetary motion. Let's go ahead and move on and talk about his second law now. So his second law, there isn't any math formula we need to know for his second law, but you need to know a couple words that go along with the second law, along with the actual second law, what it is. So here's Kepler's second law. So Kepler's second law says equal area and equal time. That's the easiest way to put it. So let's read here. An imaginary line connecting the sun to any planet sweeps out equal areas and equal intervals of time. So before we talked about cake or pie pieces. And so look, there's the sun. Here's the ellipse. Notice the sun is at a focus point, one of two focus points. It's over here. So over here, if a planet is close to the sun, how's it going to move in its orbit compared to if it's really far away from the sun? Think about that for a second. What's the difference between a planet being close to the sun, moving in its orbit, compared to being farther away and moving in its orbit? So this goes back, and this actually deals with Newton. Newton was actually able to figure out why this happens. Kepler knew it happened, but he didn't know why. So it deals with gravity. So if you are closer to the sun is pulling you around in orbit a lot faster than if you're further away. That's because the greater the distance between the two objects, the less gravity there is affecting those objects. So if a planet is here, it's going to be traveling its fastest speed, whipping around in its orbit. So let's say that this area right here, this area right here, and this area right here are all equal to 1 month. So 1 month of time goes by from here, A to B, that's 1 month time. Over here, from C to D, that's 1 month time. And then over here, from E to F, that is 1 month's the time. So here, this planet, whatever it is, traveled furthest in its orbit when it was closest to the sun. But since it's so close to the sun, the amount of space here is actually the exact same area as this one, and the exact same area as this one. So equal area in equal amounts of time. If this right here is equal to 1 month, it's the equal area as this one. If this is 1 month, this is equal area to that one and that one. If this is 1 month time, this is equal area to both of these. Equal area is traveled in equal amounts of time. That's what Kepler's second law says. So if you were, again, if you were given a piece of cake, you had these three choices. It doesn't matter which one you choose. They're all going to be the same amount of cake. That's what Kepler's second law says. Equal area in equal time. Okay? So there are two definitions that we need to know that go along with that. So take a look here. What's the difference between these places over here? So over here, if I'm over here, what's the difference between being over here and being over here? So if I'm closest to the sun, the planet is moving fastest. And if it's the closest to the sun, it's going to be in its orbit. That's called being perihelion. Perihelion. So peri means closest. Helion means sun. So when you're closest to the sun, right here, you can't get any closer because this is the orbital path. So can't get any closer. That's the closest you can get. That's when a planet is moving its fastest. A planet moves the fastest when it is at perihelion. Over here, when you're furthest away from the sun, can't get any further away because here's the orbital path going around the sun. So over here, when you're furthest away from the sun, you're moving the slowest. That's called aphelion. So when you're farthest away, that means aphelion. Ap is farthest, peri is closest. Helion means sun. Closest to the sun, planet is moving fastest. You're at perihelion. When you're farthest from the sun, you're at aphelion, planet is moving slowest. And again, the reason you're moving fastest over here is because gravity is going to pull you around faster because you're closer to the sun. More gravity. Over here, you're further away from the sun. Gravity isn't going to pull you as fast, which means you're going to move slower. It's because there's a greater distance between you and the sun, or the planet and the sun. So aphelion, perihelion. Perihelion is closest, aphelion is farthest away. Make sure you know those two definitions. So that's Kepler's second law. Equal area in equal amounts of time. Okay, third law, Kepler's third law. It's another math equation. You're going to need a calculator when you're calculating Kepler's third law. So I call it big P squared equals little a cubed. Big P squared equals little a cubed. So the big P stands for the orbital period of a planet. So think about what a period is from your physics days. So period is just the time it takes for a cycle. So for like a wavelength, it's the time it takes for a planet to orbit around the sun once. That's what an orbital period is. So you take the orbital period, the time it takes for a planet to orbit around the sun once, and you square it, and that's equal to the length of the semi-major axis cubed. We already mentioned what the semi-major axis is. So the semi-major axis is half of the major axis, and that is the average distance between the object and the sun. So length of the semi-major axis, average distance between the object and the sun. And so you take the cube of that, and that's equal to the orbital period squared. And this is important because if you know one of these, you can figure out the other. So if you know how long it takes for a planet to orbit the sun, you can figure out the distance on average that planet is away from the sun. This was a big deal when he discovered this. This is and he did this again based upon Tycho Brahe's measurements. So pretty amazing. So we're going to try some examples here of Kepler's third law. And this is just a review of the parts of an ellipse. So I went over this beginning of the lecture, but you have the ellipse, the distance across, the farthest distance across the ellipse you can go, that's called the major axis. Half of the major axis is the semi-major axis, and then you can see the two focus points. So right here, that would be the center. Another way you can put this, the semi-major axis, is the radius. It's half of it. So the radius, it's also called orbital radius sometimes. So the orbital radius is the distance of the length of the semi-major axis. And since it's a distance and length, we're measuring it again. It's measured in AUs, which is an astronomical unit. So we can calculate how long it takes for a planet to orbit if we know its semi-major axis. And if we know its semi-major axis, we can calculate. If we know how long it takes for a planet to orbit, we can calculate its semi-major axis. So it goes both ways. There's the major axis. Okay, so you need to know what an AU is. Astronomical unit. I'm not going to ask you what that means in kilometers, but I do want you to know how many miles that is. So, and you need to know the definition of an astronomical unit as well. It's the average distance between the Earth and Sun. You'll notice that for astronomy, we try to make things easy on ourselves since we live on the Earth. We try to make the numbers for the Earth as easy as possible to remember. So we're going to use us as a measuring tool to figure out distances of other planets. So we, on average, we are 93 million miles, right here, 93 million miles away from the sun, on average. Sometimes we're a little closer, sometimes we're further away. Our elliptical, our eccentricity for our orbit, we are not very eccentric. Not at all, actually. We have a very small eccentricity. One of the smallest. We are not the smallest, but we are one of the smallest with eccentricity values. And I'll show you that at the end here of this lecture. So make sure you know what an AU is, an astronomical unit, average distance between the Earth and the Sun, and it's 93 million miles. Okay, so let's try an example. And if you want to try this yourself, feel free to pause the video before I start going over how to do it, just so you can try it. I'm going to do two examples with you. And then tomorrow when we do our Kepler's activity, you'll be doing more of these examples. Okay, so let's figure out what the orbital period of the Earth is. We're going to use the Earth first. Again, I've already told you, since we live in the Earth, we try to keep things very simple for us. So you'll see what I mean with these numbers for the Earth. So if we're looking for the orbital period, that means we have to be given what? Think about what the Kepler's third law formula is. So the first thing you want to do whenever you're trying to solve any problem, you always want to write down the formula first. Always. Look at the question and then try to figure out what formula to use first. Once you figure out the formula, write it down. So we know the orbital radius of the Earth, which I've already told you, anytime you see orbital radius, that means the length of the semi-major axis, is equal to 1 AU. That's equal to 93 million miles. That's a given, because you know that. I've told you that. So we plug that into the formula. So orbital period squared equals the length of the semi-major axis cubed. So which one of these are we given and which one are we looking for? We're looking for the orbital period, which means we must have been given the semi-major axis, and we are. It's the orbital radius of 1 AU. So we plug that into the equation. We say the orbital period squared equals 1 cubed. Well, hopefully you can do that in your head. So the cube means we multiply the number 3 times. So 1 times 1 times 1. What does that equal, guys? You should know it equals 1. So the orbital period squared equals 1. So then what I have to do, once I have the orbital period squared equaling 1, I can't just keep it as orbital period squared. I'm looking for the orbital period. So if this is a square here, we have to take the square root of both sides because we were looking for just the orbital period. So the square root of orbital period squared equals orbital period. The square root of 1 equals 1. So the orbital period of the Earth is equal to 1 year. And we know that. You guys are, what, 17, 18 years old. You've been around the sun 17, 18 times. So that's your orbital period. So 1 year on the Earth is equal to 1 year, 365.25 days. The distance away from the sun, on average, that the Earth is 1 AU. I told you we like to keep the numbers very simple for the Earth. We'll try another one coming up here in just a second. All right, let's go ahead and try example number 2. So remember, guys, when we're doing this, you can pause it and try it yourself if you want, but I'm going to go ahead and continue and just show you step by step how to do this. So since we're doing Kepler's third law again, remember it's going to be the same formula. Orbital period squared equals length of the semi-major axis cubed. So let's look at our question. What is the orbital period of an object that has an orbital radius of 5 AUs? So look what we're given. That's the first thing you got to figure out. So we're given the orbital radius, and remember, radius is half. So think, what's half of the major axis? That would be called the semi-major axis. So we are given the length of the semi-major axis, which is 5 AUs. So we know that's what we're given, so let's try to plug that into our formula. So the first thing we got to do is write down our formula. So orbital period squared equals length of the semi-major axis cubed. So next we got to plug in that orbital radius of 5 AUs. So we say orbital period squared equals 5 cubed. So 5 cubed, that means that we take 5 and multiply it by itself 3 times. So 5 times 5 is 25, times 5 would be what, guys? 125. So 5 times 5 times 5, 125. And we're looking for orbital period, so that's going to be 125 years. So orbital period squared equals 125 years. But we can't stop there because we're not looking for orbital period squared. What are we looking for? We're looking for the orbital period. So how do you get just the orbital period? You got to take the square root of both sides. So if you take the square root of orbital period squared, you get orbital period. And then you take the square root of 125 years. When you do that, plug it in your calculator. Again, you're going to need a calculator, so make sure you do that. You say the square root of 125. You're going to get the orbital period equaling about 11.2 years. So that's how you do Kepler's third law. So far we talked about Kepler's first law with the eccentricity formula. We talked about Kepler's second law, which was saying equal area and equal time. And now we're talking about Kepler's third law, which says the orbital period squared equals the length of the semi-major axis cubed. So those are the 3 laws, guys. So this, I just want to show you this. This is just an animation. Now, I'm going to pull this up and show you, but make sure if you want to play with this website at home, make sure you use Internet Explorer because this is a Flash website, and the new programs, at least for me, like on Edge and Google Chrome, it doesn't work properly. If you pull up Internet Explorer, it should work just fine. So let me pull that up. Okay, so you should see, here's the website, and it just goes over the 3 laws here. What you can do is you can just play with it. So this is for Mercury. So that means that, look here, what shape do we have? So this is an elliptical orbit. This is an ellipse. There's the sun at one of the focus points. And there's Mercury right there. And so down here you can see it says Kepler's first law, Kepler's second law, Kepler's third law. And we can click on any of these buttons here. We can say, show the length of the semi-major axis. There's the semi-major axis. We could say, show the center so you can see how far off the focus is from the center. And then I can also say, show the empty focus. So there's always 2 focus points. There's the one where the sun is not. So I could do everything if I want to. Then I could show the semi-minor axis as well. But I'm going to go ahead and get this stuff off for now to show you these. You can click over here on Kepler's second law. And we can actually sweep out equal area and equal times. I'll show you that. And then there's the third law, orbital period squared equals length of the semi-major axis cubed. So let's go ahead and play with this and just show you. So the first thing I can do is I can change the length of the semi-major axis. We could do that. Right now it's at 1. So what do we know, guys? If the length of the semi-major axis is 1, what planet has a length of semi-major axis of 1? The Earth, right? Definitely. It's definitely the Earth. So we can do this. We could change it. So you can see I'm changing the length of the semi-major axis. And then when you're done with that, you can just reset it. Here, the eccentricity. Eccentricity here is 0.4. Watch what happens if the eccentricity is 0. Notice where the sun is now. So the sun went to the center of the path, the orbital path. So now it's a circle. As I move the eccentricity, notice what happens to the shape of the orbital path. It gets more and more eccentric, more elliptical, more ovally shaped. So I can reset that. Okay, let's come down here. Let's take a look at Kepler's second law here. So here I can change the sweeping pattern. So if I press this, watch what happens. So it swept out an area in a certain amount of time. So this is equal to 1/16 of the orbital path. That is. I can erase that. I'm going to reset. Okay, and I'm going to change the size. I'm going to do it for us. So we have 12 months in the year. It takes 12 months, 365.25 days for the Earth to go around once. And so I'm going to say sweep continuously, and I'm going to use a sound effect just so you can see how those sweeps are. So we're going to do it so that each sweep you see is equal to 1 month time. So watch. There you go. So from here to here is 1 month. Here to here will be the second month. There to there, third month, and so forth. So you can count how many sweeps there are, and there are 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So every single one of these colors, they all have the same area. The only difference is the distance traveled in the orbital path. So what was this called over here? When the planet is right here, notice the speed here. Watch the speed. Watch how fast it moves over here. What happens over here? Watch how it slows down. So what's this point called when it's furthest away from the sun? That's called aphelion. And then over here, when the planet is closest to the sun, what was that called? That's called perihelion. So this is just something you can do to play if you want. You don't have to, but and then this, you can actually change it. So you can see the eccentricity is 0.4 there. You can see the Earth. Press OK, and it changes it to that. So there's eccentricity 0.017. You'll notice Venus, even smaller eccentricity, 0.007. But then take a look at Pluto here, 0.249. Neptune, 0.009. So you can just play with it and see. But those are the 3 laws of Kepler. Okay, I'm going to go over one more thing. We're going to do a little review of everything of a couple of the astronomers. And I wanted to originally do Newton in this lecture, but this lecture has already taken a while. So we're going to hold off and we're going to do Isaac Newton next week. Tomorrow you're going to have a Kepler activity, but we're going to hold off on Isaac Newton for now. So let me show you, let's do a little review here. So in summary so far, here are just some of the astronomers that we've talked about. So you have Aristotle, Hipparchus, Ptolemy, Copernicus, Tycho Brahe, Johannes Kepler, Galileo Galilei, and then the last one that we're going to talk about, we haven't yet, is Isaac Newton. So think about what Aristotle did. What did he do? You need to know for him the most important thing, he had 3 lines of evidence to prove the Earth was round. Hipparchus, I call him, he's the father of trigonometry. I call him almost the father of astronomy. Very, very smart guy. He had a star catalog with over 850 stars in it, and he was correct. He ordered them by magnitude, and he was able to figure out precession as well. So he made like the first star chart that was very, very accurate and precise. Ptolemy, good old Ptolemy with the silent P. So he was able to explain his geocentric model by using what again? You guys remember? How was he able to explain the backwards motion of planets, that retrograde motion? He used epicycles. Nicholas Copernicus, he's famous for making what? He published a book on what? On the heliocentric theory. So he is the first to publish a book devoted to the heliocentric theory. A lot of people they said that he published it on his deathbed so that he couldn't get in trouble with the church, but not too many people believed it at first because he did not actually provide any evidence. Tycho Brahe, the most interesting man in the world, at least in my opinion. He partied a lot, but he was also very keen and accurate. He was very accurate and precise with his observations, discovered a supernova happen, and he did all that without a telescope. Naked eye observations using his quadrant and a couple other tools he built. Then you have Johannes Kepler, German astronomer, mathematician, astrologer, kind of a nerd, really, really loved math. And he came up with 3 laws of planetary motion. We just went over those. Galileo, the most important astronomer, the most important scientist, in my own opinion. He's my favorite scientist. He invents the telescope, 1609. Remember, there was already a toy telescope, wasn't that great, made in 1608, but Galileo makes his in 1609, and with that discovers he makes 5 observations to prove heliocentric theory. That's what he's known for. And then Newton, we're going to talk about him next week. He came up with 3 laws of motion and then gravity as well. He did a lot of other things as well. So he discovered calculus. He's a really interesting guy, kind of weird, and very unorganized. We'll talk about all that next week. But for today, we talked about Johannes Kepler and just did a little review here. So thank you guys, and I'll talk to you later.